got another U of I fellow here. Hey, let's thank Dr. Magdi Ragheb for coming in.
I am Ragheb, of course, as presented, but of course that's a joint paper with one of our students, Brandon Spencer. And as you'll see from the presentation, it has partly chemical engineering. So he's from our chemical and biomolecular engineering department. What we'd like to cover today is look at alternative cooling systems that would be associated with the thorium, particularly the molten salt breeders again. So two alternatives that we have explored in other applications is first dissociating gases, and I'll explain what are the advantages that we can get by dissociating gases as alternate coolants for liquid thorium reactors. And from a different perspective, we would like to also discuss very quickly the Kalina cycle, that's a typo here, as a cooling medium. We have applied both approaches. The dissociating gases, we used it in association with the design of a naval reactor, and the Kalina cycle was used earlier in association with increasing the efficiency of a BWR system in general. So let us see what kind of advantages we get by looking at those alternative cycles. Historically, the thorium fuel cycle was investigated over the period 1950-1976 as a liquid fuel, particularly by the people at the Oak Ridge National Laboratory. But it also did not just use really liquid fuels, it also used solid fuels. And the first reactor built to produce power in the United States, the shipping port reactor, in fact, it was the second after Calder Hall being the first in England, of course, used a thorium core. However, with solid fuels, it was a prototype for a naval reactor also. Of course, we know that the Navy has developed 9 generations of nuclear reactors, whereas, of course, the civilian sector has only developed so far maybe 3rd generation, and we are talking about 4th generation. The difficulty with solid fuels, as was met by the shipping port thorium core, is that it was very low in the neutron economy. So they had to use a concept called the seed and blanket concept, where they had to really take care of, minimize the loss of neutrons by absorptions and leakage by having them absorbed really in the control rods. That would be the seed and the blanket. The thorium cycle also has been used in the high-temperature gas-cooled reactor. That was the General Atomic Company. It built, in fact, 2 thorium reactors in the 1960s to 1970 period. One was a pilot plant, 40 megawatt electric at Peach Bottom in Pennsylvania. And the second was a 330 megawatt Fort St. Vrain, Colorado, solid fuel again. So there was, of course, experience with solid fuels and a limited experience with molten liquids, of course, at Oak Ridge. This is a quick view of course, the shipping port reactor. As I said, the first really thorium reactor built in the United States. This is a view of the Fort St. Vrain reactor. By the way, it stopped operation not because of the failure of the thorium cycle in it. It was graphite moderated, but because of a problem with steam turbines. The Germans also developed a solid type of a thorium reactor. It was the so-called Pebble Bed Reactor, shown here. In that case, you would feed pebbles containing thorium and take them, extract them from the bottom, add them from the top. Notice that most of the solid fuels, of course, used really a gas-cooled system. Helium was used in that reactor, and then the helium transferred the heat to here steam generators inside, of course, an integral type of a reactor, pressure vessel where steam was generated. One neat aspect of the thorium cycle that's not very highly recognized is that you don't need really a source of water for cooling. And that shows here the Germans using a dry cooling tower. That would be a wet cooling tower, so you need a source of water from a lake or a river. This one can be just air-cooled, that you could see it's also methanic. So in that case, thorium reactors are recognized as possibly being built away from large bodies of water in arid areas of the world, in deserts maybe. This is a pebble bed type of a reactor. It has what's called the trisofuel. The trisofuel would contain several layers of pyrolytic graphite, followed by silicon carbide, which of course is used in the space shuttle, of course, re-entry vehicles. So it can take very high temperatures, and several layers of protection against the escape of fission products. Triso here would contain the breeding fuel for that type of a reactor, and these would be little tiny fuel particles in large balls of the size of tennis balls, not even baseballs. Another approach has been the approach used in the 4-cent brain reactor. Instead of using pebbles, used basically hexagonal blocks of graphite with coolant channels for both the thorium dioxide as well as the coolant. In that case, the coolant was helium, and then the helium transferred the heat to a secondary heat generation system of steam. This is an experimental reactor built in Japan. There is another one built in China, and both of them are pioneering the Brayton cycle, or the gas-cooled cycle, using as a coolant, in that case, helium. The reason for the use of helium is that, of course, we can reach very high temperatures. However, the thorium cycle, of course, has a detriment. If we use the thermal reactors, the regeneration factor that has to be larger than 2 for breeding is very, very marginal. You find that that regeneration factor becomes very large for both the uranium-233 cycle and plutonium cycle if you use neutron energies that are quite high. And that's, of course, the benefit of using the plutonium uranium-238 cycle. So if we use a thermal reactor really like with light water as a coolant, we are operating here in that region where 2 is really barely above 2. So it's very marginal breeding. If you use a molten salt, you are really operating in that region, which even is more difficult because it's an intermediate energy reactor. The molten salt provides some moderation of the energy of the neutrons. We'll come back to this to understand why is it that it is very difficult to breed in the solid fueled reactors. And many, unfortunately, some people are still pursuing the idea of the solid fuel when in fact they are really doomed. And the reason is this. In the uranium-plutonium cycle, the way you breed, and the idea of breeding, of course, is one of the benefits or the dreams of nuclear energy, is that you absorb the neutron in uranium-238, it turns into uranium-239. Uranium-239 is unstable. It emits a negative electron, and in that case, it turns from 92, the atomic number, into 93, and that's neptunium-239. Neptunium-239 doesn't stay there for a long time. With a half-life of 2.35 days, it decays, and of course, in that case, that neptunium-239 turns into plutonium-239. So there is no problem there. It's a very short period of time where neptunium-239 turns into plutonium-239, so we can use the solid fuel. Now, if you compare it to the thorium cycle, if you want to breed thorium-232, it's a single isotope of thorium in nature, turns into thorium-233. Thorium-233 is radioactive. It emits a negative electron. It becomes protactinium-233, not 231 like Dr. Moyer was talking about. The 231 is more or less produced in a fusion type of a system. That protactinium-233 has a half-life of 27 days. So if you leave it too long in a reactor, if you use a solid fuel, that protactinium-233 absorbs a neutron and disappears. And that is really our source of uranium-233, because if you have that protactinium-233, it decays, emitting a negative electron, and turns uranium-233. So using solid fuels means, or is associated with a very, very, very marginal breeding. And the idea of breeding is really the dream of nuclear energy for the long term in general. Of course, the solution that the people at Oak Ridge National Lab found is that, well, if we want really to isolate, to produce enough breeding of uranium-233, we have to deal with a situation where we are producing protactinium-233. So in that case, you start with a salt, uranium-233, you burn it, you have another salt containing thorium, and the thorium, of course, produces the protactinium. You allow it enough time by separating the protactinium-233 out of the cycle. That will become, of course, very apparent is that of course, the solid fuel is doomed. The work, of course, proceeded at Oak Ridge National Lab. They chose and they studied it very, very thoroughly in that they built a system that was more or less a converter. It was not a breeder. They did not breed above unity. Breeding means that you produce more fuel than you consume. And that is really the promise of nuclear energy. The same ideas that the people at Oak Ridge have developed is now also the one being pursued in the molten salt reactor as part of the 6 concepts that are pursued as part of the Generation 4 reactors, except that they changed the configuration in that now we have a graphite moderator with the molten salt circulating in it. The molten salt gives its heat to another intermediate cycle here that contains another molten salt. Why? Because in the previous composition of the cycle, we had lithium fluoride. Lithium absorbs a neutron, especially lithium-6, and produces tritium. And tritium is an isotope, of course, of hydrogen that can leak through any heat exchanger. So they isolated the primary salt from the secondary salt by a salt that contains sodium fluoride. Then in that configuration, they want to produce high-temperature heat. The coolant is now transferred to a gaseous coolant. This is a Brayton cycle where you have a compressor on the same shaft as a electrical generator, and then that goes, of course, to a turbine to produce heat. The suggestion here is to use helium as a coolant. And in fact, the gas-cooled reactors are considering helium as a coolant. So basically, I'll keep going here. Helium, of course, has extremely good properties as a coolant. Other gaseous coolants that have been used is carbon dioxide. But of course, if we try to use hydrogen, it is highly reactive. It would have been a better coolant. In fact, it's used for cooling the generators in power stations because it has such a low molecular weight. It has good properties for cooling. Problem with helium is this. Helium is a very limited depleting energy supply. This is a quote from the Nobel Prize basically winner. I think it's Robert Richardson. He's a professor of physics at Cornell University. He suggests that basically we are depleting our helium supply. We don't have enough helium to run all those molten salt reactors in the future or to run even gas-cooled reactors. So we need alternatives. In that case, I suggest, of course, the dissociating gases. What is so particular about dissociating gases? Let's take an example. There are quite a few of them. Nitrogen tetroxide. If you heat nitrogen tetroxide, it turns, the molecule breaks into 2 molecules of nitrogen oxide, NO2. So instead of 1 molecule here, we have now 2 molecules of gas. Now, the ideal gas law tells us that PV, the pressure multiplied by the specific volume, is equal to nRT. N would be the number of molecules. If we had here water turned into steam, that dissociation factor here would remain as 1. Now look here what happens if you use a dissociating gas. You double PV, and PV is proportional to the work that you do in the turbine or the work that you do in the heat exchange equipment. So as a result, you double the amount of energy that the coolant can use. And in that case, you can use, of course, this shows us a very simple direct coolant cycle. You can use other combination of regeneration, as I'll show you later, and of course, topping cycles. So in that case, let's look here at some dissociating gases. Nitrogen tetroxide has an increased factor in the gas constant of 2. You double the work done per unit mass of the coolant. You find other gases. Aluminum bromide, for instance, also breaks into 2 molecules of aluminum bromide, so the gas constant factor is 2. Notice here the operational range. N2O4 is an operational range of 170 degrees Celsius. But if you go to aluminum bromide, you can really operate at much higher temperatures. I think how can I go back? Okay, here it is. There are many other types of gases. For instance, at the bottom here, gallium chloride, you can have a gas constant of 6. The fact that you can generate more, carry more energy per unit mass of specific energy of the coolant gas, other than, of course, as a replacement for helium, which is being depleted, we are using it in nuclear magnetic resonance, of course, superconducting magnets. We are using it in party balloons and so on. You'll find that we get a huge advantage when we substitute a dissociating gas to the normal steam cycle. And this is from a Russian article by Krasov. He's listed in the references. We compare here an aluminum bromide and aluminum chloride gas turbine to what you get in a normal steam turbine. So let us take this first column and the third column. Suppose that you have a turbine that produces about 500 megawatt of output power. Let's see here. If you use a steam turbine according to an existing power plant, that's 964 metric ton in weight. Now go and use this, design the same turbine as a gas turbine with aluminum chloride. Because of that property of the increase in the gas constant, that 964 metric ton is only 55 metric ton. Now if you take the amount of power here, 500 megawatt divided into the weight of the turbine, you have now a power to weight ratio of 0.52 for the water, a steam turbine plant, and it's 10 for an aluminum chloride gaseous dissociating gas. So it's a factor of 10 to 0.5, 20 times the power to weight ratio. What's the advantage here? It's like having a Lamborghini with an 8-cylinder engine compared to a 4-cylinder engine, really a small Volkswagen Beetle. All right, so you have more power per unit mass. Okay. So the advantage, of course, that was thought about it is that it was used by one of the students, and we designed basically the engine for a naval killer submarine in general. So the dramatic advantage of using dissociating gases is the reduced size of the turbo machinery. It translates into, of course, less capital cost and much compactor size machine. The size of the reactor would be very compact, so you can put it on mobile systems, on like earlier in the talks, on maybe a warship and in addition to this, of course, you have the advantage that we really would not be able to use we are not going to find helium for all our nice projects. I lost the picture on the screen here, so I have to look there. The second alternative that we looked at is the Kalina cycle. So very briefly, the Kalina cycle uses a dual fluid. It uses a mixture of water and ammonia. It was invented by a Russian scientist, Kalina, and basically it means flour. And the advantage is this: if you use really the Rankine cycle, which is a steam cycle, and you have gas here, which is really steam, you have a very limited range over which you can extract the energy from the coolant. If you use a Kalina cycle, you have a much larger range. Notice that in that case, 70% ammonia, HN3, and 30% H2O. Ammonia and H2O have very similar molecular weights, so they can exchange with each other, and they have similar properties, in fact. But, of course, the NH3, the ammonia, have a much, much lower, of course, boiling point. So you can extract the energy over a larger range. If you extract the energy from your fuel supply over a larger range, you increase your efficiency dramatically. We used it, of course, for a boiling water reactor, and we increased the efficiency from 30% to about 50%. So I'll keep going here fast, and the presentation is on the web, of course. So in terms of cost implication, dissociating gases yields lower specific volumes, enabling the construction of gas turbine units of higher capacity and lower weight. It has positive impact on the useful life of the equipment. And of course, helium as a coolant is doubtful. In fact, if you want to make a huge investment, get yourself some tubes, some helium stored that is being sold at $5 maybe for balloons, and it is suggested that the price should be $50 in general. For the Kalina cycles, ammonia is one of the most produced inorganic chemicals. Additionally, it doesn't need any new enhancements in the current equipment required. And one interesting application, of course, would be for desalination, as it was mentioned by a gentleman earlier. Today, its main success really is in geothermal heat, where you have really to extract the heat at a very low temperature in general. And it is also suggested for ocean thermal types of applications in general. There are, of course, safety implications in using ammonia, but ammonia, of course, it announces its presence, so it is somehow not that really a big problem. However, of course, we have to deal with the engineering aspects. It's like gasoline, it is flammable, and of course, it can present some fire and explosion hazard in general. So the suggestion is really for us, if we are going to deal with the new generation of thorium types of reactors on the basis that the existing uranium-plutonium cycle basically is in a rut. It's running in its own place. If we go and develop a new generation of reactors, is to go all the way and, of course, explore all the different types of new approaches that really knowledge that we have and technology provide us with. What we are doing here is, of course, what people call now the big data approach to, of course, science making. They like to call it societal physics. And I will quote Bucky Fuller, the inventor of the geodesic dome concept. We never change, let me read it, anything by fighting the existing reality to change something, build a new model, and make the existing model obsolete. And that's what we want to do about uranium-plutonium cycle. We want to make it obsolete and start anew using the latest of available knowledge to us. And I thank you for your attention.
Can you speak to the corrosivity of some of these novel dissociating gases?
They're not novel, they're very old knowledge. It seems that the Russians studied them thoroughly. We think that they may have used them on some of their Alpha class submarines that really were made out of hull of titanium, and they were faster than any American submarines. They didn't care about the noise they were making because they could outrun any American submarine. They have, of course, totally retired those reactors because they were lead cooled and they needed to keep them warm 24/7, and they ended up corroding, so they took the cores and dumped them in the bottom of the Barents Sea. So for a master thesis with one of our students, we looked at using them for the engine of a killer submarine, not ballistic type of submarines that would be too large. And of course, the higher acceleration, power to weight ratio allowed it to go 30% faster than any other submarines. The gentleman went to work for the Navy, and we didn't publish the results. So, yeah.
or comment about the upper temperature limit of stability of NO2. When the N2O4 dissociates, in the heat exchanger to nitrogen dioxide radicals, as long as the walls of the heat exchanger and turbine blades are passive with oxide layer like zirconium dioxide or whatever materials we use, the NO2 radicals are perfectly thermally stable for the short time that they're at 600 or 700 degrees C. And when it falls apart, when it goes back through the low pressure end of the turbine and cools down to below, let's say 200 degrees C, then it heals back to a dimer. So you had a temperature range that made it look like you could only heat them up to 300 degrees, but in practice, nitrogen dioxide and nitric oxide are kinetically stable, even though they'd like to burn up if they found hydrogen.
Okay, well, I respect your opinion. Obviously, these cycles need to be thoroughly studied, and there are so many different alternatives. So you don't need just to use a direct gas-cooled Brayton cycle like I've shown. You can use cycles with recuperation, and you can also use topping cycles. For instance, you can operate with the aluminum bromide as a high-temperature or cycle, and then reject to heat to the nitrogen tetroxide as a low reactor cycle. And there are so many different combinations. And you can even not need, in fact, the two cooling branches in a molten salt reactor like the generation 4 one. The intermediate cycle is really to isolate any tritium created from lithium-7. But it's easier to isolate the tritium in a gas, so it can also lead to improved turbo machinery. And it's just ideas like when you have seen the part on the alloys of thorium that needs to be explored. It hasn't been explored yet. And thanks for your comment.
Very good. All right, thank you again, Doctor.